to this webinar. I hope you can hear me fine. Just as Franca already said, in case of any questions, any problems, anything you can't see on the screen, also just use the chat box. We muted you by default so that we have low extra voice on the line, and hopefully everybody can hear me well. All right, I thought I'd start with brief introductions. This is about myself, Christian Lemon. I'm a computational chemist. I did my PhD at the German National Research Center for Information Technology. And then I went on a little tour through biotech and the pharma industry, starting with a small biotech company called Combichem. This was located on the West Coast in the US, and then acquired by DuPont Pharmaceuticals and later on by Bristol Myers Squibb. So I went through the different stages from very small to big pharma. At that point, I decided to go back to Germany and found with some fellow researchers from the academic institution the company Biosolve IT, which I did in 2001. And since then, we develop software for drug discovery, me and my team. And today, I'm going to share with you some of the latest developments. But before we start with that, after having introduced myself, it would be great if you share a little bit about yourself. What is your background? And Franca will open a poll about this in a second.
Yes, the poll is open, and we would like to know if you're a computational chemist, medicinal chemist, biologist, crystallographers, or something which we did not cover yet. If you want to precise it to me, please write me in the box. And so we see that 80% of you nearly did take part already. So I'm going to give you about 5 more seconds to make your click, and then I'm going to close the poll in 5, 4, 3, 2, 1, and this is closed now. So, as you can see, most of you are computational chemists, and the biggest number on the second place are the medicinal chemists.
Okay, very good. I think you have to close the presentation of the poll. And switch back to my presentation. Thanks for sharing this information. It's always interesting to know the audience's background. So this helps me tailor a little bit my presentation according to your perceived interests. All right, so what we want to do is searching a so-called knowledge space with feature trees. The overall goal behind this is we want to combine the capabilities of one software to do scaffold hopping and do de novo design, but have implicit synthetic access. And the rest of the presentation is going to show you step by step how we want to achieve this overall goal. First, maybe a little detour through the traditional approach to de novo design. You probably have all heard at some point about the various different approaches like splitting compounds into fragments, the well-known recap rules, or our friends from the University of Hamburg have come up with a set of rules to split compounds into fragments called bricks. And then typically after splitting comes joining fragments again according to certain rules. But then there are other de novo design approaches like more or less artificial compound transformations, like adding methyl groups in all sensible or less sensible places, doing MedChem transformations in an automated fashion, tweaking compounds, and coming up with something like the compound depicted here, which may have some desired properties, but can typically not be considered a very nice molecule, and is also synthetically probably not that tractable, and having lots of issues with it. Any of these traditional de novo design approaches can typically generate lots and lots of virtual compounds, but mostly chemically infeasible trash, which led a little bit to the problem of de novo design in general, namely that it is perceived as an idea generator, but not necessarily something that is of direct practical use. And we want to change this. Then splitting fragments, we want to capture the chemistry know-how in the company, in the academic group, in the public domain. There's lots and lots of know-how of reaction schemas that more or less routinely and robustly allow you to combine certain reagents and form larger products. And you see here indicated by the numbers that we really aim at doing this large scale, so many reactions to be captured. Once we have captured the reactions and pre-processed, and I'm going to go into some level of detail about the pre-processing, we have arrived at a chemistry space that potentially contains billions of virtual products. What we show here is actually not whole molecules, but just fragments of the molecules. And again, I'm going to show you in the pre-processing how we arrive at this chemistry space. And then in the next step, we give you the ability to take a query molecule, that might be your competitor compound or your natural product that you start with, your current lead structure, you name it. That is your starting point of a search. And now you can go into the chemistry space and using the similarity search method called feature trees, retrieve compounds that are similar to the query and result from these reaction protocols. So synthetic access implicitly guaranteed through this way of searching and the way that the search space is built. And I start now my presentation in this last part, the feature tree similarity, because we believe that you must understand how the searching is done to then be able to do the next step and just follow us how we do the pre-processing and arrive at a space that allows this kind of searches. Okay, so feature trees is a similarity descriptor. And on this picture, you see two molecules, a query compound and a virtual hit. And I overlay now the feature tree that represents, or the two feature trees that represent these two molecules. And as you can see from the overlay, the feature tree, as the name suggests, is a tree structure. It doesn't contain any cycles. Any cycle in the original molecule graph is condensed to a single node. So rings are always represented by single nodes or broken into multiple nodes, but always under the assumption that no more rings can be found in the graph afterwards. These nodes, they have different sizes and colors, and you can already guess what the meaning of the colors is. It should represent that the properties of the underlying chemical structure differ. Yeah? So we have an aromatic ring here, we have an aromatic ring here as well, but also in addition donor and acceptor feature. We have an alkyl chain here, we have an acceptor feature here, we have an even stronger acceptor feature here, and so on and so forth. So we have this quite crude description of the molecules, but how do we arrive at a similarity from that? And the heart of the feature trees method is a so-called mapping calculation that maps the nodes of one feature tree onto the nodes of the other feature tree. Yeah? And every time I have a map, like from this node onto this node, I can compare locally what are the properties of this node. Okay, aromatic ring, so and so big, quite hydrophobic, and so on and so forth. Maps very well, so it has a local similarity of, say, 0.9 to the other node. And from the local similarities of all these matched nodes, we can calculate the average, and that is the similarity associated to this mapping. And the beauty of the feature tree method is that it is fast enough to generate from all possible mappings the one with the highest similarity value. So this mapping leads to the similarity 0.81, and that is the highest possible similarity between the two compounds that you can find for the feature tree method. Now, we have the representation of the molecules, the local properties, and through the mapping, the overall similarity of the molecules. And we can make use of that for the user, for the end user in the output by displaying, for example, color-coded on the 2D graphs of the molecules, the mapping, so that the user can see, okay, feature tree mapped this ring onto this ring, and so on and so forth. The walk through the graph. Here, for example, you see a ring mapped onto an open chain part in the other molecule. Okay, interesting. You get the local similarity values and the overall similarity as well. And you can even carry that further on and translate the mapping also into a 3D overlay by generating multiple conformers of both molecules and overlaying them according to the mapping in order to find out what is the best fit in 3D. So this is, in a nutshell, how the feature tree method works to describe the molecules, to calculate the mapping, by the mapping, generate a similarity and what kind of output you can expect as a user. And the next few slides are to show you a bit of the characteristics of feature trees. What you see here in this picture is a query molecule on top of the list, and then we did a search of this query molecule against a database of compounds. We gave every active molecule against the same target as the query a black stripe here in the list of compounds sort ordered by similarity. And from this expansion of the top 2% region, you can see that we have quite a few of black stripes. So these are all active molecules. So you see an enrichment for active molecules in retrieving active molecules. But more importantly, you see how on rank or list position number 2, 3, 4, which is actually rank number 3 and rank number 22, quickly the similarity of the chemical structure starts to differ from the original. So here's again the query molecule, and the most similar compound found on rank 1 with this similarity value. It is really quite similar. It has this extra chlorine and it has a different attachment position on the double ring here. But other than that, it is quite similar, and you can imagine how the feature tree nodes of the query molecule compared to this molecule ranked second look alike. But even just a little bit further down the list, rank 22, similarity 0.899, you see differences, a nitrogen missing, the connection between these two aromatic ring, between the aromatic ring and the saturated ring here in the middle gets a little bit longer. Here also a donor position missing on the ring, and so on it continues. So quickly the chemical structure differs, while feature tree still sees some decently high similarity value associated with the compound. From the black stripes you can see that indeed all these molecules are D4 agonists, so they are all active against the same target. So feature trees is capturing some of that biologically relevant similarity, but you can see here this one key characteristic, namely that feature trees is able to jump to different chemical classes quite quickly. This next slide here shows how people have compared feature trees to other descriptors. So we have the daylight fingerprint, probably everybody knows this similarity method, Unity, holograms, CATS, MoldPrint2D are different similarity descriptors, and on one target class in this publication they have calculated retrieving using the different active molecules as queries, how high is the average enrichment? Yeah, and here feature trees is 1.27, whereas daylight similarity really performs a lot better. But the whole point in this analysis, and why I mention it here, is while feature trees typically has enrichment values or delivers enrichment values that are about on average the same as other similarity methods. This column here is most important, the number or percentage of exclusively retrieved molecules by this one method. And feature trees really sticks out here in usually in comparison giving you the highest fraction of exclusive hits. So from those retrieved active molecules, 43% were found only by feature trees and not by the other methods. And that is something that comes really out nicely in this publication, and they have reiterated this over a number of targets. This is a quite busy slide, but I encourage you to take a look at that publication and learn more about this exclusivity ranking. And here's another slide illustrating the kinds of results people have achieved using feature trees. What I want to point out is not so much the fact that, yes, indeed, active compounds against the target of interest were found, and this was published. But you see this scaffold hopping capability. Here's an open chain structure in the query, and here's a ring closure in the hit molecule. So this difference in topology from query to hit molecule is usually the striking difference. And again, the fact that leads to feature trees oftentimes retrieving different orthogonal results compared to other methods. So that concludes my little feature tree description. It's a quite crude or fuzzy descriptor, which leads to its scaffold hopping capability. It provides comparable enrichments, but very orthogonal results. So if you combine this search method to different other search methods, then you add a lot of value, definitely. The mapping itself adds value as well for the user. You can see in 2D and realize quickly why something was found to be so and so similar. And in 3D, oftentimes things that look alike in 2D don't make any sense in 3D, and you can quickly weed out unwanted results once you go to 3D. And we have quite a few successes with the application of feature trees documented. All right, that leads me to the next question, which is about your primary use of drug discovery software today. Again, asking a little bit about your background. What do you use drug discovery software for today primarily?
Yes, and we give you the following options to choose. Do you normally generate new compound ideas when you use the software? Or do you use it for prioritizing new compounds and deciding which ones to make? Or to get a better understanding for rational design? Or designing new compound libraries? Or do virtual screenings of vendor catalogs? So please think about it and choose what you normally do. If you have anything else which is not on the list, please write it to me. And at the moment, half of you did already choose, so please make your choice. And we need maybe some more clicks. So, okay, I would say thank you for choosing, and get you the results here. Most of you use it for generating new compound ideas or get a better understanding for rational design. And I get back to Christian.
Okay, thanks a lot for this feedback again. And let me continue my tour through this deck of slides, reiterating for you our ultimate goal. We want to combine scaffold hopping and synthetic access. I have showed you feature trees, which is the responsible party here for the scaffold hopping capability. I hope that I could show you that it does indeed have this capability to find scaffolds with decently high similarity that are chemically quite distinct. Now we can look at the second part, which is the synthetic access. The motivation is quite clear, I guess. If you just look at the in-house compounds, depending on the size of your organization, this might be quite an iceberg, but certainly it makes use only of the tip of it. A lot of people then, as a second resort, see what's purchasable elsewhere, and that's a quite sizable chunk of the iceberg in addition. But what we want to do is really lead out from there, from the purchasable compound space, by applying virtual chemistry and really making use of these gigantic blue ocean of new chemical matter that just waits to be used and uncovered by you. How do we do that? Here comes a quite busy slide. I built it for you piece by piece about this pre-processing chemical reactions into a chemistry space. So typically a combinatorial reaction protocol looks somehow like this. You have reagents with functional groups that using one or more steps of real chemical reactions to be combined into products like this one. Yeah? And we now rebuild this chemical reaction definition in a Lego type fashion. Yeah? It starts by extracting the core, and on the core identifying the functional groups and replacing those with so-called link atoms. These are dummy atoms that are like the attachment points on Lego pieces, built so that things can be stuck together. We do the same identification of functional groups on the reagents, and also equip the reagents with these link atoms. And as you can guess from the colors already, not everything can be combined with everything, but only what is feasible according to the reaction protocol can be linked. Of course, we don't just have these 3 reagents given in the picture, but typically stacks of reagents from your in-house library or vendor compounds. And we do the same trick, of course, for all of them. And then we unify the reagents to remove any duplicates, and then store them into a pre-processed set of fragments and a set of rules. The rules are really very simple. What I already showed in terms of the color coding, L1 is compatible to L2, L3 is compatible to L4, and L5 is compatible to L6. So these are the connections here in this picture. And so far this matrix looks trivial, but of course if you start merging now multiple reactions all into one chemistry space, then this matrix gets more busy and more complicated, because you don't want to store redundantly the fragments over and over, but just a single copy representing a certain reagent. But as a user, what do you have to do to define a reaction protocol so that all these steps on this busy slide can be done automatically? You provide a reaction-based description, yeah? And here we have a reaction table with input files and the actual reaction sketch, and showing one as a close-up, you see how this typically looks like. You have your substructure definition that identifies the fragments from the reagent pool that are relevant. You can use tricks like naming functional groups, and hidden underneath is of course a smarts definition for these names that you can use that make the reaction much more human readable. And you have the reagents defined here and the product definition on the other side of the arrow. And typically the only extra step that is needed so that the whole busy transformation definition that you have seen on the previous slide can be performed automatically is the mapping of atom IDs from the left-hand side to the right-hand side. So just via these atom mappings, the procedure is then automatically able to clip the reagents, attach the linker atoms, and maintain the rules that say which fragment can be combined with which other fragment. So that is the input that you provide as a user. And now, how does this fit together with feature trees? It's really very simple. I have shown you how a feature tree represents a whole molecule. This is not a molecule, this is a fragment with these linker atoms, but of course you can imagine that this can be represented using a small piece of a feature tree, and similarly another fragment with another linker atom can also be represented as a piece of a feature tree with these special feature tree nodes for the linkers. And same as we know in real chemical structure space, what is compatible to what. We know the link compatibility rules also in feature tree space. So from these two pieces, we can build the larger feature tree piece according to the rules. And we can go back to the original molecule after combining the two. So this is what's called fragment assembly, and that's the crucial thing that leads us to the ability to take a query molecule and search in a virtual chemistry space that is not an enumerated product space, but really contains only these small feature tree pieces that can be plugged together to form real molecules according to the reaction protocol. So the search algorithm goes now through these pieces and finds and assembles the pieces according to similarity to the query. Yeah. So this is bringing now the two worlds together. The reaction definition led to the virtual chemistry space, and the feature tree search algorithm is able then to take a feature tree query, build the feature tree pieces or put them together that resemble the query as much as possible, and then translate that back into molecules, so that as an end user you get product molecules as a result. Okay, after having built such a space, and we did this with quite a few pharma companies in the past, the big question at the beginning was, okay, how do we know that this actually works? Because the one thing we realized right away is that enumerating these chemical spaces is impossible, because the size of the space is easily within the billions of virtual products. So you can't just write them all on disk and then do a traditional search and be sure that you are finding the right thing. So to test the searching routine, we thought, okay, we can enumerate a few sample products that we know are in there, that belong to the chemical reaction definition, and retrieve how many we find back by using the similarity search method. So from the billions, this is not a trivial exercise, but as you can see, from close to 1,000 random queries, we were able to retrieve 90% of the molecules that we knew are in there, with an extremely high feature tree similarity, 0.99, and 99.9%, so almost all of them, were retrieved with a slightly lower similarity value. And there's a reason why the similarity value for a product that we know is in there is not necessarily 1. It is value number 1 for the large proportion of cases, but due to some frictional losses in plugging together the feature tree pieces, this is a little bit a lower number, but that is an impressive retrieval rate of close to 100%. So after having done the virtual validation, yes, whatever is in there, we can find with a high likelihood, even though there are billions of virtual products in there. In another publication, colleagues from Pfizer did a search in a similarly big space that they were able to publish for us. So this was a search for 5-HT3 antagonists, and this is the query compound. And as examples, you see 4 search results retrieved using the feature tree search method in this big space. And it's quite interesting to see that, yes, indeed, it is not a search by chemical library or so, but it is really searching across the board, because among the search results, you find ether forming reactions, a urea and a amide forming reaction, all giving you feature tree similarities that are pretty high, 0.97, and a little bit lower than that. So from different chemical libraries came these virtual products. And what is interesting as well is, for comparison, you see here the daylight and the pipeline pilot calculated similarities for that same pair of molecules, query and virtual hit. And these numbers are quite low. Yeah? So not only is it impossible to search through all these molecules, 10 to the power of 12 molecules, with a traditional similarity metric, but also with such moderate similarity values, you would have no chance to find hits like that. And again, from a publication from the colleagues from Boehringer, they also had quite some success using the feature tree search method in and searching in their big in-house space. And I don't have the time to go into much detail with this method. Just to tell you, it was quite successful, and it also captures a huge virtual space. Yeah, the two success stories in two different target areas, again documented here, and you get the slides, so you don't have to write any of that down. All right, but that brings me to the next poll. And that is, again, asking you for your experience. This is rather wishful thinking. If you had a ghost, what would you like it to accomplish for you, or what would you value most in a drug discovery software?
Yes, and it's me again, and I'm going to read to you the options you have. Would you like more support to work with multiple proteins, or do you have a purpose to visualize CH acidic H bonds, sigma anions, holes, and so on? Or are you looking for instant information about nearby known compounds? Or do you wish for better support to generate project status reports? Or do you look for water happiness ratings? And if you're looking for anything which is not in the list, I'm happy to have your opinion. So, and half of you did already choose. So I'm hoping for some more of you to make a choice. So let's say about 10 more seconds. 8, 7, 6, 5, 4, 3, 2, 1, and I'm gonna close this poll, and here you see the results. Thanks for choosing, and most of you obviously support to work with multiple proteins.
Okay, interesting result again. Really to not only work with one protein, but usually fighting multiple devils at the same time seems to be high on the wish list to have better support for. Thanks again for this input, and I can now continue my story. Again, the ultimate goal, combining scaffold hopping with synthetic access in de novo design. Again, in the first part of the presentation, I've told you much about feature trees' capability to do scaffold hopping, and in the last part of the presentation, I talked about chemical libraries, how to capture them to have in a virtual chemistry space synthetic access encoded by design and by definition. And now let's see what we've got in terms of that. So we designed a new, what we call knowledge space, that is such a chemistry space as I outlined on the previous slides. Some of you may have read a publication from the Schneider group. Actually, Gisbert Schneider is a well-known author in this area of virtual chemistry and capturing chemical libraries. And from his publication a few years back, we took 57 robust combi-chem style reactions that are routinely used in many labs around the world. We had a knowledge space I call it here the old knowledge space, designed some 6 to 8 years back. Part of the reactions, after careful reviewing it, this was a space of 82 reactions, about half of them we discarded in light of what is possible with feature tree searching, and we retained 42 of the reactions. And then we added textbook chemistry reactions, 21 of them right now. This is still work in progress. So in total we have a 120 chemical reaction in the new knowledge space, captured from the literature, so available to the general public. We also took reagents from trusted compound vendors. So these are available compounds as well. All of that is in the public domain, and we are going to provide this new knowledge space, and not only the space but also the tools to build it. And the tools to build it, I'm going to talk a little bit more on the next few slides. I start with the chemical reactions. I want to give you a sense for what types of reactions are captured in the space. Transformation reactions like this Strecker reaction, which transforms an aldehyde to an amino acid. That is in there. Substitution reactions like this nucleophilic substitution reaction, that is in there. We have additions like this epoxide forming reaction captured in the space. And we obviously also have these multi-component reactions. Part of the fun of the virtual chemistry space searching is, of course, the large numbers of virtual products that can be captured. And through these multi-component reactions, typically many reagents come together, form these product molecules, and lead to a nice and sizable space. So this gives you a sense for the reaction, and again, you see these mapping numbers. That is really the input that you provide as a user. So there's no extra magic behind it, just a drawing of the reaction, and the only extra step is providing these mapping numbers. Everything else works automatically behind the scenes. Currently, taking recent vendor libraries, this leads to 6 gazillion virtual molecules. I don't know what the precise naming convention for a number with 16 digits is. So really an enormously big space. In the reaction selection, we were aiming at something that's giving us new scaffolds. We didn't want anything that gives us panes, so-called panes structures. We went at quite some length to filter out any panes substructures or substructures leading to panes in the products. And we had an emphasis on the solubility of the products because this is oftentimes deciding about the real applicability of the reaction or not. But what we give to you here, the 120 reactions as of today, shouldn't be seen as the end point. It can be seen as the starting point, because new reactions can easily be added, and you for yourself can decide which ones to include really and which ones to discard. We just provide a starting point for you. Similarly, what we consider a trusted vendor may be different in your organization. So the reagent list can obviously replaced, expanded, modified. And all we do here is KNIME embedded, and I have 2 more slides on that part. So the KNIME embedding, it starts with massaging the input. So from a standard file reader, be it an SD reader, a MOL2 reader, SMILES reader, some database connection or so, we first of all filter reagents mostly down by size and complexity, so that if they undergo the reaction, we don't end up with 1500 Dalton and bigger compounds, stuff like that. So we rather start small with the reagents. We also have paints filters here, as I said, salt stripping and the usual routine of cleaning up compounds. All of this is, of course, configurable by the user. You can tweak it according to your needs. Then the second step is the actual reaction processing. Yeah. So in your sketcher, which can be one from a number of drawing programs, in KNIME embedded natively, there's the Marvin sketch node. So we took that for our design of the knowledge space. So here comes in your reaction, and here comes in the reagent, the filtered reagent list. And then it goes into a so-called enumerator node, and for every reaction you kind of do that separately. So the enumerator is kind of validating and enumerating reaction products at the same time. And you can, of course, take a look at the reaction definition and then look at the output of the enumerator, the enumerated products, and validate this way that the reaction definition does what you expect it to do, i.e. the products it generates are looking right. And then as the last step, we have a merger. You can merge these outputs from the enumerator nodes, but you can also merge together a previously generated space together with some extra stuff that you want to include in the latest incarnation. The merger actually generates the fragment space, and then a chemical file writer writes the space. Reactions that you want to include or discard, merge it all together and write out a fragment space. And this is just a picture of an example workflow that shows you how in KNIME you can make use of such a space. So here's a fragment space reader. That is the pendant of the writer node from the previous slide. So once you are done with generating the space, here you read it. Here's again a sketcher node that allows you to draw your query molecule, and then from here in this single node there's the feature tree fragment space searching. Typically you want to remove some more unwanted structures, so we have a cleanup node here. And then here's your table viewer for visual inspection, but you can also proceed and take the search results, for example, to a docking node, and then take a look at the results in 3D. So that is a very typical application workflow. I have used this workflow myself on a number of structures just taken from the PDB. Take the bound molecule, search in the fragment space of similar compounds, similar according to feature tree similarity, then dock all the molecules in the PDB and take a look at the result in 3D. And you can, of course, also think of refining compound ideas in later rounds of design. Namely, if you find something of interest here, you may want to do some modifications and then feed it back again into the search cycle. So that is easily possible. And that brings me to the concluding slides. And let me reiterate the few take-home messages that I want you to take from this presentation. So feature trees can help your chemistry project early on to identify novel leads in parallel or after an HDS, so that you are sure that among the available compounds you really have everything captured that might be of interest for your project, and late in the project as well to identify backup candidates. So in all different phases of a chemistry project, feature trees can be super helpful. I said it is giving you comparable enrichments, but it is definitely also giving you some distinct and exclusive similar compounds compared to other methods. And then the second part is the knowledge space, the virtual chemistry space searching. It gives you a lot of benefits. You can save a lot of time by its per definition incorporated chemical access, chemical synthesis. The whole basis of the method is capture chemical libraries, so that is incorporated. You can make sure that your in-house chemistry know-how is really thoroughly explored, and through a few documented successes with Boehringer, with Pfizer, and we have a few more literature examples like that. You can see that this is a highly successful method. So that concludes my presentation. I just want to highlight that we provide not only software but also services. If you want to let us conduct a drug discovery research project for you, check out our website or write us a message telling us about your interests. So that is an interesting option. And also I want to point out that once more, you get a trial license, everybody who attended. You also get the material and the video recording in an email soon. And we have the next Biosolve IT webinar coming up in March 23rd, that is, where we will show you a tutorial style introduction to CSAR, which is our flagship product. So with that, I'm through with the presentation and I'm happy to take any questions.
I have one question to pass to you from Kathy, and she wants to know how FTrees uses the 3D shape of known ligands, and if the knowledge about the conformation can be fed into the results.
Yeah, that is a very good question. Let me jump back in my presentation to a slide that allows me to address that question in detail. Wait a second. All right, now I've got it. All right, so I want to come back to this slide. So feature trees is really in itself a very crude description of the molecule. And while you see on the 2D depiction the feature tree overlaid, really feature trees does not know anything about orientation. It does not know where these acceptors are pointing and where this donor is pointing. All of this information is invisible to feature trees. But as I pointed out here, we can take the mapping which leads to the feature tree similarity value, in the case of these two molecules of 0.81, and translate it into 3D by generating multiple conformers for these molecules and then providing the user the best scoring overlay in 3D. So only in this post-processing of the feature tree result you will really have 3D information captured. Otherwise, I have to say that feature trees oftentimes also benefits from being such a fuzzy and crude description. Yeah? So it's a fine balance. You as a user can choose to either work with the similarity alone, or if you want to use the 3D alignment and the 3D similarity value as well for further filtering.
I have a second question to pass to you from Raul, and he asks if feature trees can be represented externally in some kind of feature smiles way, or are they only some internal binary data structures?
Yeah, in fact, feature trees can be stored to a file, and the file is a human readable ASCII format. Yeah, there's no magic or hidden information in a binary. What it looks like, this feature trees file, is a little bit like an SD file. It has even positions for the nodes. But most importantly, it has a little feature profile to every node. So from this ASCII description, you can in principle, well, first of all, make a drawing like that, but also decipher which nodes are in there and which properties do these nodes actually have. Yeah? So it would in principle be possible to take the feature trees information and feed it into a different method that does the mapping calculation in some different way or so. Yeah? So in principle that's possible. It's no binary file format, it is ASCII format, but admittedly a little bit techy. Yeah? So this is not the most user-friendly interface, I would say.
Okay, in this case, I guess there are no more questions. I would like to thank Christian for his talk and you for attending our seminar. And we're looking forward to see you on the next webinar.